Hello everyone, welcome to our presentation. My name is Prem Shivakumar. I'm the technical lead for this product, and this will be a joint presentation with my distinguished colleague Anup Gangwar. And we're going to be talking about NI700, which is a configurable network on chip with novel automated tooling scaling to hundreds of interfaces. Here is a brief agenda for the presentation. I'll start with an introduction to NI700, and then I'll talk about some key hardware features, and then I'll hand it over to my colleague Anup, who will explain the tooling suite and the various components of the tooling that help aid design, performance, and reporting. And then we'll end with the summary and conclusions. Now for a quick introduction to NI700. Firstly, it's a fully distributed interconnect. Because of its fully distributed nature, we are able to achieve high operating frequency, around a gigahertz or plus. At the same time, we are able to achieve low latency of 1 cycle per block. It's also a highly configurable microarchitecture, and this enables us to support different use cases that may be there for different market segments, and also a wide range of PPA, where in some cases very low power and area is critical, whereas in some cases you want to achieve the maximum performance. Finally, it's also scalable to hundreds of interfaces. It supports an advanced feature set, and I'll be expanding upon that in later slides. And with something that has such a highly configurable microarchitecture, ease of implementation that supports a faster time to market is very important. And there are 3 key aspects to this. There is advanced automation that is delivered with the product, which supports multiple modes. It also has support for early PPA analysis. And finally, the product is delivered verified with other ARM IPs that includes CPUs, GPUs, memory management units, etc. Right? So now let's dive into each of these different aspects. So starting with the distributed interconnect. The picture on the right shows an example topology of an NI700 interconnect, and you can see that it has multiple clock and power domains. The blue rectangles represent the protocol bridges that interface with the external AMBA protocol. The blue circles are the routers. They can also be upsizers or downsizers that natively upsize or downsize between different link widths in the interconnect. And the blue hexagons that are divided into 2 halves are the power and clock domain crossings, which are also natively supported in the interconnect. So the protocol complexity is contained within the protocol bridges at the edges, and these are the components in the interconnect that translate from the external AMBA protocol to the internal packetized protocol that we call generic transport. And internally, NI700 implements a packetized wormhole routed interconnect where the packets are further broken down into flits. And the flow control between components in the interconnect is credit-based flow control that allows us to be more scalable. In terms of routing, the route vector is determined at the source, at the protocol bridges, for the entire path through the interconnect from source to target. And because we have a route vector, we are able to support ad hoc topologies. So we can support a mesh, we can support a tree, or any ad hoc topology. And the tooling comes with integrated checking for transport level deadlocks, so that what you build is inherently deadlock free at a transport level. NI700 also has support for multiple virtual channels to provide non-blocking access. So this is the fundamental building blocks of the distributed interconnect. Now, once you have a wormhole routed interconnect, one of the key aspects is your link scalability. At the AMBA protocol interface, at the AMBA interfaces, we have support for data widths ranging from 32 bits all the way up to 1024 bits. Once it gets converted from the external AMBA protocol to generic transport, which is a wormhole routed interconnect, the flit sizes we support all the way ranging from 32 bits for something that meets a very low PPA, all the way up to 2K bits for some use cases that might need very high performance. And these flit sizes can be independently configured for each channel. The picture on the right shows 4 different types of packets corresponding to different channels. You see the request channel that contains the protocol, the link layer header and the protocol header. And there is a response channel, which again has the physical and the link layer, but also has the transport or protocol layer information. And then you have packet types that contain response with data or data only. Once these different packets are broken down into flits, you can, depending on the size of the flit, you might be able to send a packet as a single flit, as shown in the diagram on the right, or you can configure the flit sizes so that a packet is broken down into multiple flits. So this gives you the flexibility to determine your flit size based on your bandwidth and PPA requirements. The flit sizes can also be independently configured for each virtual channel to optimize the overhead of virtual channel flit buffering. And they can also be independently configured for different sections of the interconnect. And NI700 natively supports upsizing and downsizing of flit sizes within the interconnect. An additional flexibility or support that we have with links is if you need even higher performance, you can have duplicate links between any consecutive transport components. You can support up to 8 duplicate links for higher performance. On the other side of the spectrum, we can actually share links to have even more optimal PPA. So you can share the read and write request, or you can share the read and write response channel. Now we have talked about links. So now let's look into the microarchitecture scalability. NI700 supports up to 128 requesters, up to 127 targets. We support high frequency. We can go up to 1.2 gigahertz at 7 nanometer. And of course, this really depends on the configuration that you're supporting. So depending on the configuration, you can either go higher or lower, depending on your PPA requirements. At the same time, we are able to support very low latency, a minimum latency of 1 cycle for each of the individual components. We also support build time configurable pipeline stages, and this allows us to support even higher frequencies and or deeper structures by trading off latency. To allow achieving high performance, the trackers, the data buffers can go up to 256 deep, and NI700 has native support for up to 32 power, clock, and voltage domains. And finally, we have support for advanced address mapping, which supports both non-hashed and hashed address regions. Now, this is just a snapshot of some of the key features that are scalable, that allow a wide range of PPA. Now, if you look at architectural aspects, we have support for multiple AMBA protocols. So at a high level, we support ACE5 and ACE5 Lite. We have native support for AHB5 and AHB5 Lite. And we also support ACE3 and ACE5 Lite ACP, but only on the master network interface or the connection to the downstream target. And we also support APB3 and APB4 at the master network interface. Now, within each of these AMBA protocols, there are many sub-features that can be enabled or disabled depending on the need of your configuration. I'm not going to walk through all of them, but just to call out a few. For example, in ACE5, we can support atomics, we can support read data chunking, we can support different flavors of cache maintenance operations. In AHB, we have support for exclusives, for extended memory attributes, for burst promotion, etc. And NI700 allows native bridging between these different protocols. So we support cross-protocol interactions between ACE, AHB, and APB. Now looking a little more into the architecture support, we have a robust support for quality of service. Now in an interconnect which can support so many interfaces, master and network, slave network interfaces, maybe supporting different traffic classes and priorities, quality of service becomes a very key feature. And it has in-network QoS-based arbitration. We have QoS regulators at the source to be able to tune the bandwidth and/or the quality of service. We have support for QoS accept at the master network interface. And finally, you can have secondary control over quality of service just using your tracker capacities, your virtual channels, duplicate links, etc. One of the key availability features NI700 supports is called Interconnect Device Management, or IDM, which has support for not only timeout detection and error logging, but also is capable of recovery. On the debug, we have support for silicon debug monitors, ACELite trace, and performance monitors, which allow performance profiling. And finally, on the RAS side of things, we have support for transporting data parity, or ECC, through the interconnect. Now, hopefully this gives you a flavor of the distributed nature of the interconnect, the scalable microarchitecture, and the architecture support. Now I'm going to hand it over to my colleague who can talk about all the advanced tooling features that enable ease of implementation and faster design time.
NOCs are special in the way that they require a robust tooling suite to be used effectively. In the next couple of slides, we are going to describe the tooling suite for the NI700 product and show how it's complete by itself and also extremely useful for the designers to be able to design the NOC effectively. There are several components to the tooling suite for a NOC. The first one, of course, is the way in which it enables the design. Then the way in which the analysis of the generated NOC can be carried out. And this is the performance analysis as well as the reporting structure. Then what is the collateral which it generates in order to enable easier integration with the other flows? And finally, is there an easy migration from any of the existing designs to this NOC? For the NI700, the designers can either choose to do a full custom manual design enabled through the Socrates environment, or they can use a behavioral synthesis tool, NoC-SE, which takes input as input a physically aware behavioral specification and generates the NI700. Or they could make use of scripts, and we have a Python-based scripting environment, and this is quite helpful in case there's a very regular structure as an example, if you can generate a tile and just stamp it out repeatedly. Finally, any of these designs which have been generated, especially the ones generated by NocSC, could be refined either using the manual flow or the scripted one. For the performance analysis, there's a tightly correlated performance model to analyze the performance. And it also has a variety of traffic generators, which the users could tweak, including the burst sizes, the rate at which the transactions are inserted as well. Then a several set of scenarios are generated by the behavioral synthesis tool NocSC based on the user supplied inputs, and these could be used in the performance model. Also, the users could supply their own traces in the M3I format and run those to see how the NOC is operating. For reporting and collateral, we have machine learning based area models, which enable one to quickly estimate the area of the generated NOC. And this is quite useful when one is doing a refinement based on the performance data and they want to estimate as to what is the area impact. A variety of reporting is also included, such as the static latencies, the component usages, etc. The generated collateral contains, along with RTL, test benches, SDCs, placement information in the form of a tickle dictionary to enable the rest of the flow. For ease of migration, there are extensive DRCs at every level, as well as there is a harvest flow which converts a NIC-based configuration to a NI700. Finally, to ease the migration, there is also ability to read in floor plan and the memory map from a CSV file. The Socrates environment wraps all of the tools together and presents a unified environment for the users to use all the tools. Here is a screen grab of the Socrates environment as presented to the user. This is a physically aware canvas where each of the cells represents 100 microns. And of course, this 100 micron can be chosen by the user to be a different number, and the floor plan would be adjusted accordingly. The routing channel, the unroutable areas, the interfaces, and all of the components which have been approximated to lie on the 100 micron boundary are present here. Users can use this environment to either do a full custom, that is a manual design. They manually place the interfaces, the routers, the SerDSs, PCDCs, connect them, create the routes, and everything. The users have the ability to configure all the aspects of the design. So since this is a full custom design flow, everything is done by the users. There's a real-time feedback on the timing closure. So suppose, say, if there is a path or a route which is too long, as one can see here, which has been marked as red, the tool gives real-time feedback that there is some issue here in terms of the path length, and the users would need to insert a pipeline slice in here. There's a last set of DRCs which enable one to make the changes and still feel confident that there are no issues in the design which has been created. Taking the layout restrictions into account while configuring the IP has a benefit of greatly reducing the later iterations during the P&R stages. Generating a NOC by hand is a fairly involved exercise. In a very small 16 interface cross 16 interface design, which has 4 clock domains, as the user can see, there are more than 4 billion possible RP assignments, 100,000 topological choices, 65,000 clock domain assignments, and a similar number of link size assignments. If one were to put all of these together, the design space is huge. And that is where a tool like NoC-SE, which is a behavioral synthesis tool, comes to the designer's aid. What it does is it takes as input a behavioral specification. The user needs to supply the locations of the interfaces and the unroutable areas, their sizes, all on the physically aware canvas in Socrates. the traffic along with priority, latency, peak and average, etc., and the power and clock domain properties. The tool operates based on a large set of approximation algorithms. It optimizes and tries to match the performance goals while still keeping the area less. So it tries to do a very balanced PPA optimization. And out comes a fully laid down NI 700 where all the routers have been created, they have been put together, the virtual channels or the resource planes have been assigned, the power and clock domain converters have been inserted, the links have been sized, and the certus is inserted. Along with that, there's also an integrated placement engine, which would move the components around and try to minimize the pipelines which need to be inserted. And it will move them around and then finally insert the pipelines in order to meet the timing. Also, it generates traffic scenarios which the users could use with the performance model. In case of a fairly regular design, where the users can just design one small area and maybe stamp it out, or in order to better enable integration with the other flows, we also have a Python-based scripted design and refinement environment. So user is able to programmatically construct the NI 700, define the high-level specification, design features, or they could even invoke NocSC through the same API. The execution is lightning fast, even on large designs, and it scales very well to the capacity of the NI 700 product, which is 128 cross 127 interfaces. The interface is quite flexible, and the users can very easily use it to either refine or generate a new one. Here is a brief snippet of the script using the API. And here it shows how you could just create the interfaces, then update them, add the blockages, move them, and do a variety of other things. And based on just this script, here is the NI 700 which has been created. There's a whole bunch of static reports which are generated, and these include the static latencies, the component utilizations, and all. In order to study the dynamic behavior of the generated NI 700, we also bundle a performance model, which is highly correlated with RTL through a performance app into the Socrates environment. The users can use any of the three different stimuli mechanisms. They could either supply their own traces, or they could use the inbuilt transaction generators, which allow them to configure all the aspects of a XC transaction, or they could use the performance scenarios as generated by NocSC. They could tweak the target BFM response latencies and a bunch of other parameters. The performance model will run using this as stimuli on the NI 700, and it will generate a whole bunch of statistics. Rather, it includes all the PMU events, and these are present in the detailed log. For example, the bandwidth or latency for all sources and targets or between pairwise source and target. The link utilizations or buffer occupancies, and these are quite useful when one is trying to zoom into a problem when the performance is not being met. This performance model enables a very tight refinement loop so that one can just very quickly observe the performance, make the necessary changes to the NI 700, refine the design, and then rerun in the performance model till one is satisfied of the performance. Here are two screen grabs of the perf app, and these are what we call as the logical view. There's a router, and these are all shown as circles with the connectivity, and the throughput and the latencies are reported in here. There are a whole category of other views, which of course we cannot show here due to the paucity of space. The last component of our tooling suite, which we describe, is the area models. Whenever a user is trying to refine a design or the first design which they create, a very important question is, what is the area which this design is going to occupy on my die. Or if they make a change to meet the performance, they would like to know the area impact of that change on the design. And this is very important for parameters such as the link sizes, which could actually increase the area significantly. That is where the area models come into picture. The goal is to predict the approximate area in microns square for the design created using any of the mechanisms. We have separate models for the various components, that is the routers, the various bridges, the SerDeses, PCDCs, etc. And these have been trained using unit level RTL synthesis over several tens of thousands of configurations. It's based on artificial neural network for training and prediction, and as well as we incorporate the design of feedback on the RTL parameter impact. And this is a very high level view of the whole setup. Here is the trained model, which is bundled along with the Socrates environment. And while using, the user just press a button within the environment and out comes the area report. This screenshot is of the area report, and whereas it's not quite visible here, here are the top level numbers, and here are the reports in terms of the distance which signals are traveling.
Thank you, Anup. Now to the conclusions of this presentation. In the beginning of the presentation, we demonstrated how NI700 has a very scalable and highly configurable design. We talked about how it's a fully distributed microarchitecture. We talked in detail about the link scalability. We also talked about how the different microarchitecture features, including the number of initiators and targets, the different structure sizes, are highly scalable, all adding up to a highly configurable design. And what this enables us is to be able to support different use cases with a wide range of PPA requirements. At one end, you might have a design that has very low bandwidth and or prioritizes low power or low area, and we are able to support that. And on the other end of the spectrum, you might have very high performance designs which need a very wide link width, or very deep trackers, or a large number of initiators and targets, and we are able to support that. Then we talked about the advanced feature set that spans a number of different areas, and some of these are listed below. Support for AMBA protocols ranging from ACEI, ACELite, HB, and APB. We talked about quality of service features, which is very critical for such interconnect designs. Low power, native support for multiple power, clock, and reset domains. And we touched upon availability features in the form of interconnect device management and debug support in terms of performance monitors and silicon debug registers. Then my colleague Anup walked in detail through the different advanced tooling features which enable ease of implementation and faster time to market. He walked through the different advanced tooling modes that include a manual mode, autosynthesis, scripted modes, etc. Early PPA analysis can be quite critical to determine whether a particular design meets your performance and area requirements. And NI700 tooling is fundamentally physically aware. That speeds up time enclosure. It comes with integrated performance feedback and an integrated area model with reports that let you analyze whether this is a good fit for your use case. And finally, the fact that NI700 is verified with other system IPs gives you greater confidence to be able to take it to market. With NI700 establishing a strong foundation, it allows us to plan future enhancements in various areas, and some of these are listed below. We're planning support for future AMBA protocol versions with newer features, enhanced support for quality of service, address mapping, and reliability, availability, and serviceability, and higher performance are just a few areas where we're going to focus. And that brings us to the end of our presentation. Hope you enjoyed it. And thank you.